So that one you have to use the so-called skin stick model. So I want to went through that very quickly last time. I want to mention that only two things you need to be very careful when you are using ANSYS to do skin stick model. This is a stick, this is a skin. So for skin, you need to use shear element, shear 28.8, something like that. 288. I remember shear something. I don't remember that number. Okay, 288. I remember shear. You need to use shear element for the skin, and line element for the stick. Okay, so you need to create the geometry, create the line first, and then use those lines to form the area. Then they can be a whole geometry, whole structure together. Otherwise, they will be falling apart when you apply the load. Okay, so you need to create a line for each stick first, and then use these 4 lines. You can create 4 lines for this area, right? And use these 4 areas to form. Use these 4 lines to form an area, and then create that area by area. You can create the whole geometry, and then you can mesh the whole geometry. But when you are trying to do the mesh, you use shear element for the skin, use line element for the stick, and then you can apply the boundary condition, apply the loading to do the analysis. I do not ask for the script file for that problem, so you can use GUI. For that one, you can use GUI. Okay, if you are not comfortable with GUI, you can use GUI to do this analysis. Just create a line, an area, and do the mesh, and show me the contour. That is what I want. Okay. And for this one is hand calculation. Why hand calculation can only deal with cross-section, section by section? Why we cannot do that analysis of the whole structure by hand? Because we have infinite number of cross-sections along the beam member direction. But ANSYS can show you the distributions along this member length directions. But we are doing the analysis of this cross-section. This is a cross-section. When you look at that cross-section, so this is the boom area. When you cut this beam along this cross-section, this is the boom area and this is the boom area. The boom areas are different. And what is the shear center of this cross-section? What is the shear center? Where is the shear center for this cross-section? We don't have to do the calculation. It's in the center because total symmetry, right? Should be here. So shear center should be here, and you can put your coordinate here. Z, Y. Okay? And then what is the direct stress? So called the normal stress along this direction. This is the length direction. And what is shear flow in each skin? We have formula for that. Actually. So we have IYZ is 0 because it's symmetry, right? And Vy is 0. The loading is only along Z direction. So for direct stress, sigma x is reduced to My Z Iyy. This is a formula that we can use to calculate the direct stress acting on the boom area. And then what is y? What is the moment about the y-axis on this cross-section? The loading is not acting on this cross-section. The loading is acting on the end of this beam. So what is the moment about the y-axis on this cross-section? Should be the force times the distance. 100 kilonewton times the distance from the force to this cross-section. So My should be negative or positive. And this is force. This is y-axis. When you look at the direction, it's clockwise. Right? The bending is structured like this way. So when you look at this bending from y direction, it's clockwise. That is why it's negative. So negative 100 kilonewton times 2 meters. 2 meters is the distance between the loading plane and the cross-section you are dealing with. So it's 200 kilonewton meter minus So this is the moment acting on that cross section, and then IYY. For this cross section IYY, again we use the formula is AI ZI squared. I is the index of the boom. We have 6 boom areas for this cross section. So we use the coordinates of each boom area and use the area of each boom area. You can calculate it. Actually, they are symmetry. So 4 of them are the same. 900 times 300 square, and the other 2 are the same. 2 times 1200 times 300. 300 is 1/2 of the total height. Total height is 600 millimeter. So we're using the length unit to be millimeter. So this one you will get 5.4. This is second moment area. Then sigma x equals to my z IYY. Y is negative 200 kilonewton. We convert kilonewton to Newton, and then convert the meter to millimeter, because we are using millimeter for IYY. For consistent to be consistent in the length unit, we'll convert everything to millimeter. Z is the coordinate along z direction for each boom area. So you can simplify this. This is a general formula for sigma x, each boom area. Each boom area will have a different z, and then you can get different sigma x with different boom area. So boom 1, when we look at boom 1, z equals to positive 300 millimeter. This is boom 1. This is, I put it here. This is boom 1, this is boom 2, this is boom 3, 4, 5, 6, Y, Z. Total height is 600, total length is 1200. So for boom 1, Z equals to that much. And you can calculate the force acting on boom 1. F1 equals to sigma x 1 times A1. We are calculating what is the force acting on this stiffener along x direction. This is a cross section, it's a stiffener, right? What is the force along this direction? Sigma x is a stress. Area is 300. Area is not 300. Area is 900 millimeter squared. So this is the force acting on boom area 1. And then you will get Z1, A1. Right? It's equal to 3.7. Z1 is 300. And A1 is the area of force boom, 900. So you will get a force. It's 100 kilonewton. Yeah, when you do the calculation, it's in terms of Newton, and then I convert this force unit back to kilonewton again. Yeah. So this is the force acting on boom area 1. You can do the same calculation for boom 2 and here boom 6. Use the same formula, okay? Same sigma x2 times A2. And sigma x3, A3, and here sigma x6, A6. Because sigma x, you have the formula, it's a function of z. Each boom area have different z, each boom area have different A. You get different force acting on different boom areas. So this is the direct stress. And then what is the shear force? What is the shear stress? So shear stress 1, 2, 3, 4, 5, 6, S, Y, Z. What is the shear flow in the skin? And the formula, again, we can use is sigma QI equals to VZ IYY AR ZR. When the cross-section is symmetry, when you only have shear force along Z direction, this is a formula for us to calculate what is the shear flow in the skin. And then what is VZ? What is VZ? Can we use the external loading? This is the initial setup. This is the initial setup. This is the force acting on the tip of the beam. This is the cross-section we're dealing with. And in that formula, we're using a shear force acting on this cross-section. It is simple 100 kilonewton. It's not. It's not. You have to use what you have learned in mechanics and materials to calculate what is the shear force acting on this cross-section. And then use that value for the formula. There's some detailed procedure in the textbook. Okay. You can refer to how to calculate VZ on that cross-section. It's in magazine textbook, 5th edition, page 335. On this page, you will see how to figure out what is the shear force acting on this cross-section. You are supposed to know this from what you have learned in mechanics and materials. I'm not going to explain that. You can use force balance and moment balance to figure out what is the VZ in that cross-section. It is 666.6 kilonewton. So in this cross-section, we cannot simply use the force acting on the tip, because that is not the section we are dealing with. We are dealing a cross-section in between. We have to figure out what is the shear force on that plane. So that is the value we should use for sigma Q. 666, 10 to 6 Newton. And IYY, same value. IYY is 10 to 8. This one is Newton. This one is force order. And AR, ZR. This is the formula for the shear flow. And then we deal with booms one by one. So first one, we begin with boom 6. Okay? Use this formula, we begin with boom 6. And shear flow from here from 6 to 5, Q65. From 1 to 6, Q16. Okay? I got a question this morning. What is the sign of Q65? What is the sign of Q16? You don't know what is the sign yet. You just assume some direction first. It's going outwards. Assume if it is going outwards, it should be positive. If it's going inwards, it's negative. But when you finish the calculation, you get something negative sign here. Then this direction should be flipped. Just like what you have learned in method of joint for tensile and compressive force. From a joint, if you put a force going outwards, that means you are applying a tensile stress, a tensile force on that joint. If you put a force going inwards to that joint, it's a compressive force. For shear flow, same thing. You assume in shear flow, outwards is flowing outwards, it's positive. Inwards, negative. That is why for this summation, Q65 is positive and Q16 is negative on the left. Okay? Only two shear flows. One is positive, one is negative. And then use that formula. A6, Z6, right? We are dealing with boom 6. So is equal to Q, can be derived Q65 equal to Q16 minus A6 is the area of 6 is 900 millimeter, right? And Z6 6 is below y-axis, should be negative. Z coordinate of 6, the 6 boom area, so this one is negative 300. It's below y-axis. So this is how we use this formula. On the left, you use the summation of the shear flow. Some of the shear flow is positive, some of the shear flow will be negative, okay? And on the right, you use the area and coordinate. This is how we use this equation. And Q65 equals to Q16. Just simplify that equation. This is a solution. I just simplify that equation as second term. I just calculate it. This one is in terms of Newton millimeter. So this is derived from the Higgs boom area, and you do that for the Higgs boom area. This is Q65, right? You still assume shear flow is flowing from 6 to 5, and some shear flow is flowing from 5 to 4. So again, on the right, on the left, something going outwards, positive. Something going inwards, negative, right? For that equation, two shear flows. And you have some number here, you have some number here, but here is A5, Z5. This number is that VZ. This number is IYY. Okay. And A5, Z5, this is area and coordinate with Higgs boom area. So you can further derive Q45, Q54 equals to Q16 plus I'm trying to write everything in terms of Q16 because this is a closed cross-section. There's one unknown there, different from open section. For open section, you can begin with free end. You can solve one by one. But for this, everywhere is closed. So you can only write shear flow in terms of some unknown. Here, unknown is from the shear flow from point 1 to point 6. So this is second equation we have. Do this one by one. You'll get Q43 equals to Q16. And Q32, Q16. Equals to Q16. So when we look at this cross section again, 1, 2, 3, 4, 5, 6. Right. So everything, all of the shear flow in the scheme are written as a function of Q16. So this is unknown. 65 is the first line. This one. So you have everything. All of the shear flow are written as a function of Q16. And when you check this, when you check the symmetry, so 1, 2 should be symmetry with 6, 5, right? 6, 5 is that much, 2, 1 is this much. Forget about the sign first at this stage, because you do not calculate the Q16 yet. You do not know what is the sign. But look at the form. This one is the same as 6, 5. This one, shear flow in this section is the same as what we have for this section, because they are symmetry. Right? And when you check the symmetry, you can verify, you have a sense the derivation is correct or not. And then you have one unknown. We need to calculate that unknown. So this is the shear center. BZ is there. we can use the moment balance about this shear center. Ms equal to 0. Okay? And what is on the left is a moment contribution from the external loading about the shear center. Right? Shear center is a point that we're going to take the moment about. And on the left is a moment from the external force contribution. Vz is acting on that shear center. So there's no anything on the left. On the right is a contribution from the shear flow. Okay? Shear flow, 1, 2, 3, 4, all of the skins of the shear flow. Those shear flows are contributing to the moment about this shear center. For example, for this one, I'm using, if this one is loaded as Q12, okay, there's a shear flow flowing from point 1 to point 2. Q12 will be negative Q21, so do not have to worry about that. But when you check, what is the contribution of the moment about point F, point S? This is the shear flow. Shear flow is the force, right? Force times the distance. You get a moment contribution from that shear flow. Shear flow is force per length. You need to times this shear flow with the length and then times the height. The general formula is Q12 A12S 2. This is a general formula they can use. No matter that skin is a straight line or curved, you can use this formula. Shear flow is the flow shear force flowing in that skin, and this is the area. This is the area surrounded by those 3 points. 3 points. When you have 3 points, you can form an area. No matter it's curved or straight line. Okay? When you have 3 points at least. You have 2 points, you cannot form an area. But when you have 3 points, you can just simply form an area. Just connect them. Okay? So this is a formula that we can use to calculate the moment contribution from the shear flow. And we do that one by one. 2, 3, A23S. For this one, right? Q23. Right? So until 2Q61S. You have 1, 2, 3, 4, 5, 6. You have 6 shear flows to worry about. You have 6 terms on the right. And you have 6 areas. Actually, these 6 areas are the same. No, not the same. This one is different. Right? Q43S, that one is different. So the area could be different. The area is determined by those 3 points. 3, 4S, you can form an area. 6, 1S, you can form an area. If the area, if one of the edge, straight line is easy to calculate. If you have a curved line, I give you some information. I give you some information in homework. Okay, so you can use that information to calculate the area. And this is what you have on the right. You can use what you have calculated for shear flow. Q43, Q32, Q21. Q21 is equal to negative Q12 is equal to negative Q21, right? It's equal to negative Q16 minus 33.2. There's only one unknown on the right because we are going to write everything in terms of Q16. An area you can calculate it. So only one unknown, one equation. And you can from this equation you can derive Q16 equals to negative 97 millimeter. Only one equation, but you only have one unknown. This is easy because you already figured out what is the shear flow every time. Just be careful about those areas. Okay. So and then you substitute this shear flow Q16 back all of the other shear flows. You can figure out what is the shear force flowing within the skin. This is a procedure. In ANSYS, you can calculate the whole structure, not just one section. So you can check your ANSYS calculation by take one cross section out of your simulation results. When you finish your answers calculation, you have the results for the whole structure. Or if you want to check one cross-section and then verify that result, use your hand-calculated result, is possible. But I didn't ask you to do that in homework. Okay? So this is how we are going to use this hand calculation in realistic wing structure. And actually, wing structure is more complicated than this. Next one, we're going to introduce a little bit more complicated wing structure. So
it's not symmetric.
It's something like this.
Makes sense.
The final project, we are going to deal with something like this, but just use axis. Okay, this is one typical, more realistic wing structure. Where it is more realistic, you have several closed cells within the cross section. This is just one cross section. Okay, when you just cut that wing, realistic wing, you will see some internal structure like this. This is called front spar. And this is called rear spar. And this is still skin. And this is stiffener. Why this kind of structure is more complicated to be analyzed? Because it has several closed cells. If you only have one cell, we can use the procedure we have derived in the previous two lectures. But here we have three cells. Okay? Each cell will have different shear flow. Each cell will have different direct stress on the bone area. We need one more equation. We have more unknowns in this kind of structure. Okay, so maybe I just do one example. You will understand this better. The equation is still the same. It's symmetry. It's symmetry about y-axis. This is z-axis. So it's symmetry. So that equation can be reduced for direct stress and also shear flow. That's this shear flow, we still can use the Qi equals to Vz Iyy AR ZR. Equation, we still can use these two equations in terms of equation, but we need one more equation to derive the shear flow. If you just use these two equations, you will not be able to solve all of the shear flow in the skin. So what is the additional equation that we can use? Moment balance. We always can use moment balance. There's one more equation that we can use. When you have 1, 2, 3, we have three different cells within one cross section. It implies when you apply loading, bending, or moment on this structure, these cells has to be deformed together, right? Otherwise, the whole structure will be falling apart. So when you apply a torsion, twisting, this is the length direction. Bending or pushing this way, or this way. No matter what kind of loading I'm going to apply on this structure, all of these three cells should be deformed together. That means the rotation, the twist angle should be the same. Twist angle. Three cells should be having the same twist angles. So what is the twist angle definition? D theta dx equals to, I gave this formula last time, is 2a q ds gt, right? This is a twist angle for one closed cross section. dx along this direction. This is a wing structure. Cross section like this. You apply the torsion in this way, right? Along this direction, each cross section will have a different twist angle. Will have a different theta. But within each cross section, these three cells should be twisted together, right? This is one cross section. Within each cross section, each cell, all of the cells, all of the closed cells, you have 3 closed cells. All of the 3 cells should be twisted together. That means d theta dx cell 1 equals to d theta dx cell 2 equal to d theta dx cell 3. This is defined as cell 1. This is defined as cell 2. This is defined as cell 3. We can have as many cells as we want, but this is just a typical example, 3 cells. All of the 3 cells should be twisted together. And then we can figure out what of the shear flow. So I'm going to introduce one example. You can understand better how useful this situation will be. So a typical wing structure, but in the previous lectures, we do not have any spar. This is a wing structure we did with before. Now I'm going to put a spar here to make it more stiff. So this is a wing structure, and we have some boom areas. Each boom area has the same value, 10 centimeters squared. And this is 1, 2, 3, 4, 5, 6. And thickness is also uniform. Why I'm giving you a thickness? Because I'm going to calculate twist angle. When you look at the formula of twist angle, you're going to need T. T is the thickness of the skin. Okay? So this 2 boom area is different. This one is 25 centimeters square. This one is also 25 centimeters square. This is 10. This is 10. And also this one is also 10. From here to here is ½ meter. Here to here, 1 meter. Here to here is 1 meter. And the loading is applied on the 5th boom area. Is 8,000 Newton. And the height is 1/4 meter. T is uniform everywhere, it's the same, and shear modulus is 27 gigapascal, and Young modulus is 70 gigapascal. And this is not a circle. This is not just 1/2 of a circular area. This is elliptical area. So the area of the ellipse is we can use. It's still the same because it's symmetry. So this equation is always valid. The symmetry about y-axis. Okay. And in order to use that formula, we need to calculate IYY first. IYY is still using the same formula, AI ZI squared. You have 1, 2, 5, you have 6 areas. Just do that one by one. That one will be 8.5. This is IYY. And then we need to deal with the areas, room areas, one by one. So we start with, this is Q54. We start with the fourth area. The fourth area is in the middle of this arc. So you have Q54 there, and also you have Q43 there. This is a two-shear flow associated with the fourth boom area. And on the right, on the left, Q43 positive, going outwards, and 54 inwards, so negative. And then on the right, VZ is 8,000, so 8,000 Newton, okay? And IYY is 8.5937 into 5 meter force order. And then what is the area A4? What is the coordinate Z4? We're dealing with the force boom area. So this one is Q43 will be equal to Q. What is this for the first area? 0, because that cross section is symmetry about the first area is here, right? The symmetry about the y-axis. The first area, z coordinate will be 0. So it's 0. Z coordinate is 0. And you can derive Q43 will be equal to Q45. So this is the first equation we have. And you can do the second one. For the, this is 3. This is the third boom area. Q43 was going inwards. 2 is here, so Q32 going outwards, and you have another one here along the spot. So it's Q35. So use this equation again. You can write Q35 equals to Q54 minus Q32 plus 29100. I skipped the procedure. Okay, I'm just using that equation to do the balance of the shear flow. You have 3 terms, so that is why you have 3 terms here. I'm going to write all of the shear flows in terms of this one and this one. You will have 2 unknowns. You will have 2 unknowns to figure out, different from the previous examples. We only have 1 known, but now you will have 2 unknowns. All of the shear flow can only be written as a function of 4, 5, 5, 4, and 3, 2. Okay, so do that area by area, and Q1 equals to Q32 plus, so this is a Q21, and Q16 equals to Q21 equals to Q32 plus 5,800, and Q65 equals to Q32. I skipped some procedures, okay, because they're the same. You just use that equation one by one. You will get this. And now when you check all of the shear flow, 1, 2, 3, 5, 4. All of the shear flows are written as a function of 4, 5, 4, and 3, 2. 2 unknowns. If we want to figure out all of the shear flow, we need to figure out this one and Q54 also. So what is the equation that we can use? The first equation we can use is the moment balance. That one is still there. Moment balance is still there. So suppose we use moment balance about 21, we'll get one equation. But we still have two unknowns. We need one more equation. We have two cells. d theta dx1 equals to d theta dx2. This is the second equation we can use. We have two equations, two unknowns. Which two unknowns? Is Q32 equals to how much? Q54 equals to how much? We need to figure out these two unknowns, and then we can figure out what is the shear flow. We need to use two equations for the two unknowns. This is precision. If you have three cells, you have one more equations. If you have three cells, you will have three unknowns. But you have another equation. The twist angle of the second the twist angle of the second cell will be equal to the twist angle of the third cell. So this is how we deal with this kind of multi-cell cross sections. Okay, and then we derive this from the first equation. What we can get? This is the first point. Second point here, 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 here. 1, 2,